Hey, how's it going? I just wanted to do the same problem that I just showed you, but sort of show you another approach to it, okay? I like this approach, and I only learned it in the last couple of years, but oh well. I wish someone showed me this before. Um, you've got this situation where a car is already moving with a particular speed, with a particular velocity at 0 seconds. So it passes you with a speed already. It's already moving. And the car smoothly speeds up. So the velocity time graph, you'll recall, looked like this, right? And this is our initial velocity, right? If I trace this over, this is our final velocity. I'm going to leave out numbers, if you don't mind. I think you'll see that it's really useful. I'll call this t, okay? And you'll remember that the area under a velocity graph, this triangle, that area, plus this rectangular area, together make the displacement, okay? So the rectangle area is v naught times t, initial velocity times time, okay? And initial velocity has a direction. You're moving in a particular direction, all right? This triangle here, well, its area is going to be 1/2. Base would be t, and I guess I could call this height my change in velocity, okay? I'll use the symbol triangle for change, v for velocity. And change in velocity has direction since initial velocity and final velocity have a direction to them. You're always, anything with velocity in it has direction attached to it. So that's what these little arrows are that we put. And in this example, you're going to see this principle is going to become very important. It becomes a very powerful way to look at these problems. So if I add these two areas up again, that's this total area, which actually is in the shape of a trapezoid. The total area is going to be these two areas added, all right? So what you get in the end with this total area, the total displacement, and displacement is a vector that has direction. It's a vector that starts at the position you start and ends at your final position, okay? And then your initial velocity has direction to it, okay, times t, plus, now, I'm gonna write this a little different. Sorry about that. Let me fix that. I want to put it like this. T times v naught. And then here I'm going to write half of t times my change in velocity. Okay? And I can make this equation a little bit cuter if I refer to my acceleration graph, which should look like this, right? And you'll recall that this area is my change in velocity, all right? So change in velocity is going to be whatever my acceleration is times whatever my time is, okay? Oh, that was cute. Whoops. Let me fix that. Okay, so this is going to be a times t. And acceleration has a direction to it, just like change in velocity has a direction to it. The direction you're accelerating is important. The direction you're accelerating combined with the direction of your velocity tells you if you're speeding up or slowing down. Positive acceleration isn't always speeding up. Negative acceleration is not always slowing down. It's the direction of velocity and the direction of acceleration together that tell you if you're speeding up or slowing down. Anyway, all I want to do here is plug in AT for delta V, okay, to make this equation a little bit nicer. The full equation then becomes change in position equals T times V naught plus 1/2 T times acceleration times time. So that's what I plugged in there. And acceleration has direction. Okay? So let's simplify this a little bit. And this is usually how you see this equation written in textbooks. Although I rearranged the terms a little bit. You'll see why in a little bit here. The 1/2 T squared, because T times T is T squared. So we got 1/2 T squared, and that's times our vector A. Okay? So what very few people realize about this beautiful equation, they see these arrows over the symbols and that's not that important. Well, it is that important, man. It's telling me that I have a vector called displacement, and it has a magnitude and direction to it. All right? Now there's two vectors that add together. This one and this one. Now, I have an initial velocity vector. Let's say this is my initial velocity vector. But it's scaled to be bigger or smaller by whatever t is. If t is 1, my v naught vector stays how it was. But if time is 5 seconds, 6 seconds, if t is a number bigger than 1, this v initial, velocity initial, my initial velocity vector has to get bigger because it's scaled up by a factor of whatever the time is. On the other hand, if my t is a number less than 1, my arrow gets smaller. So whatever t is changes the size, the magnitude of my initial velocity vector. So in this example, initial velocity was to the right. But it's scaled, it's changed size by t. And then this vector adds to my acceleration vector. My acceleration vector was in that direction as well. But my acceleration vector is made bigger or smaller according to whatever 1/2 t squared is. If 1/2 t squared is a small number, less than 1, this vector gets tiny. If 1/2 t squared ends up being a number bigger than 1, my acceleration vector gets longer. But the direction does not change. The direction of this vector, 1/2 t squared a, it's still in the direction of my acceleration. So I'm talking about this one. So my 1/2 t squared makes my a vector bigger or smaller. Okay? And all the rules of adding vectors work perfectly here. The length of my displacement is going to be the length of my v naught vector scaled by t placed head to tail with my 1/2 t squared A vector. So these two vectors in black, placed head to tail, add to a new vector that goes from where I start to where I end, that is my displacement vector. That's the vector in red. The vector in red is equal to the two vectors in black added together. Okay? Now you can see how we would solve this problem. No, you probably can't see yet. Well, the problem becomes very simple. You see, you knew that V naught in this problem was 3. It was 3 meters per second. You knew that T was 6 seconds. You did not know A, right? You knew delta X, though. Delta X was, I don't know, 108 meters, right? So, using this vector relationship, you can solve this so simply. I'll redraw the vectors. So I got my delta X vector that I know is 108. I'm going to leave out the units because I have them over here. My T times V naught vector, so if I multiply T times V naught, I get, what, 6 times 3? I get 18. So that's a little itty bitty vector compared to 108. So I'll draw 18 there. That's 18 long. So the numbers tell me the length of the vector. All right? Now, T is 6, so T squared is 36. I take half of that, and I've got 18. So I've got a vector here that has to go all the way to there. That's 18 times my acceleration long. Okay? Now, the length of this vector here, this blue one, this second one that's 18A, the length of that one has to be 108 minus 18. Do you see why? From here to here is 108. There is 108 minus 18 is going to give me my blue vector that's 18A long. So 108 minus 18, I could do that in my head. It's 90. So 18A has to equal 90. 18 times my acceleration is 90. So that means if I divide by 18, I get A equals 5. I'll put my units back now. Meters per second, meaning that every second my object is speeding up by 5 meters per second. Now, to find the final velocity, we do the same thing. We can look at our velocity graph. It looks like this, right? And we have an initial velocity here. I have a final velocity here. And writing the equation of this line, okay? Equation of the line is y equals mx plus b. No, that's not the line. That's what they teach you in math. Anyway, y to us in physics is whatever variable is on our vertical axis. In this case, it's our final velocity. Okay? M is the slope of our velocity graph, which is called acceleration in physics. X is our time t. Okay? Initial velocity is our b term. Okay? Now, the beauty comes when you realize that our velocity has direction, our acceleration has a direction to it, and our initial velocity has a direction to it. And then you're like, oh, well, that means I have a vector, my final velocity vector. And then I have an acceleration vector made longer or shorter by whatever t is. So I have an AT vector. And then I add that to my initial velocity vector. And together, when the two red vectors are placed head to tail, these vectors add to my final velocity vector. Well, I know that my AT vector here, actually my A was 5, my T was 6, so this one's 30 long, 30 meters per second long. And my initial velocity, if you'll recall, was 3 meters per second. So I add these two to get my final velocity vector that starts here and ends here. And you can see right away that your final velocity is 33 meters per second. That's it. That's what I wanted to show you. I hope you appreciate how powerful and how useful vector representations are in physics. The idea is simply that you can incorporate direction within your numbers so beautifully with an arrow. It's an elegant, simple notation. Really works well. It'll take time to get used to it, and you'll need to practice with these problems. But you can actually solve all these problems using these vector approach. Hope you enjoyed the video, and I hope you have a good night.